Hello, the purpose of this video is to go through with you how to do a thermal energy transfer calculation. So go ahead and get out your notebook, get ready to take a few notes, and I'll teach you how to do this. All right, so first of all, let's get a better marker here. First of all, what is a thermal energy transfer? First of all, thermal energy, we know, is otherwise known as heat. Okay, so this is essentially just a heat transfer. Let's give a nice definition to it here. When two substances of different temperatures are combined, heat always flows in the same direction. It always flows from the hotter one, the one with the higher temperature, to the colder one. So heat always flows whenever there's a temperature difference, and it always goes the same way. Wherever it's hot, it goes to where it's colder. Like I said before, that is why when you're sitting in front of a fire, the heat is coming from the fireplace out to you and not your body heat into the fireplace. It always goes from the hotter temperature to the colder temperature. And you know what? Let me not finish this sentence. Let me add a dot, dot, dot and finish it here, because this part is kind of important here. That heat flow occurs until the two substances reach the same temperature. Only when the temperatures of the two substances are the same will that heat transfer stop, okay? All right, so how is this used? How can we do a calculation? I mean, this might seem conceptual at this point, but how can we do a calculation that involves this concept? So let me go ahead and show you a practice question that would involve a calculation of thermal energy transfer. So practice question here. A 77.1 gram silver block initially at 58.5 degrees C is submerged into 100.0 grams of water at 24.8 degrees C in an insulated container. Now, in an insulated container is only there to allow you to make the assumption that there is no heat loss into the surroundings. The only heat transfer will be between the silver and the water. So there's not going to be any into the air. There's not going to be any into the container. All right, so the next question is this. What is the final temperature of the mixture? And at this point, it is a mixture because you've added silver to the water. It's not dissolved, but it's still considered a mixture because it's two or more substances. Let's just go ahead and draw a little picture just to illustrate the simplicity of what we're saying here. We are literally saying you have water. The water is at 24.8 degrees C. And you take a piece of hot silver, and I'm calling the silver hot because it's hotter. The silver is at 58.5 degrees C. And you just, what did I call it? A block? All right, well, I'll make it square. You just put a hot silver block, and the silver is 58.5 degrees C. And you just put it into the water. So the question is, which way is the heat going to flow? And it is important that we think about that. Is the heat going to flow from the silver to the water or from the water into the silver? And hopefully you can realize with me that it's going to flow from the hotter one to the colder one. So the heat transfer is going to go out from the silver into the water, and I'm going to label that Q. Q is what we use for heat in thermochemistry. So the heat is going to flow out from the silver into the water. Now, the law of the conservation of energy states that energy can be transferred, but it is never created, nor is it destroyed. So one of the things that you're going to need to do for these types of calculations is understand that the heat that is lost by the silver, and when we talk about heat loss, we use a negative Q. That's a loss of heat, or a release of heat, okay? So the heat that is lost by the silver is going to have to equal exactly the same amount of heat that is gained by the water. Now, I will make the one that is losing heat have a negative, and then make the one that is gaining heat have a positive, because that just makes sense to me. But the magnitude of these two Q's have to be the same, or else we violate the first law of thermodynamics, which is quite serious and it should not be done. So this is how you set up a basic thermal energy transfer. Just whatever one is losing heat, make it have a negative. Whatever one is gaining heat, make it have a positive, and set them equal to each other. And at this point, what you can do is you can substitute in, let me get some room here. For each one of these Q's, heats, you can actually write a Q equals M times specific heat capacity times delta T. So for the silver, we're going to do a negative, because it is a negative here. And essentially the equation that I'm using here is this basic thermochemistry equation. Heat equals mass in grams times specific heat capacity times delta T. So for silver, we're going to start with the left. It's a negative. And let me just put this whole thing in parentheses. The mass of the silver, I've erased it, but I still have it here, is 77.1 grams. Now, the specific heat capacity of the silver, it is going to have to be given to you. You're not necessarily expected to know it. Let me go ahead and give it to you. Specific heat capacity for silver is equal to 0.235 joules over gram degrees C. So that would have to be given to you in order to solve this problem. So I'm going to times this by 0.235 joules over gram degrees C times delta T. Now, delta T is T final minus T initial. I am going to be solving for T final because, as you'll remember, these two substances have to reach the same final temperature. So that's going to be my variable that I'm solving for. So I'm going to put in T final minus T initial, because remember, that is what delta T is. And the T initial of the silver is 58.5 degrees C. Okay, that is going to be the left side of my equation, the negative Q. Okay, now that I'm taking up quite a bit of space. Let's go ahead and I'll just do this really big, and that's going to equal, now let me set up the right side of my equation. I'm going to have to write it down here, but you should just write it regular. The right side of my equation is going to be the same thing, but written for water. So the mass of the water was 100 grams, 100.0 grams, times the specific heat capacity of water, which is 4.18 joules over grams times degrees C, times delta T, which is T final minus T initial. So once again, T final minus T initial, which in this case is 24.8 degrees C. Okay, so now let me go ahead and erase some of this stuff that I don't need. And once again, the specific heat capacity of water would be given you. At this point in the equation, it's just a matter of simplifying. Now, it's much easier. What I would suggest you doing is just get the product of these two numbers first. So 77.1 times 0.235. And at this point, I think it's probably just best to understand that all of your units are going to cancel. The grams are going to go away. The grams are going to go away. The joules are going to end up canceling each other, and just your temperature is going to be in degrees C. So you can kind of let go of your units for a little bit because these get a little bit complicated. So let me just simplify this equation. Don't forget that that's a negative. I'm just getting the product of these two, and I'm just going to do that. 18.119. Now, I still have to times that by T final minus 58.5. So let me just kind of write that in there. Okay. And that's going to be equal to the product of these two. So 100 times 4.18 is 418 times T final minus 24.8. Okay, so I'm just kind of simplifying, taking one thing at a time. Now that you've dealt with this first unit, you're going to have to use, it's called in algebra called the distributive property. When you have a number multiplied by something in parentheses, you're going to have to do this number times T final, and then you're also going to have to times it by that second unit. Okay, so let me go ahead and carry this on through the next simplification. Keep that minus there. We'll deal with that in a little while. 18.119 T final, so I've just multiplied it by the first, and I'm dealing with the negative later, so let me not worry about that yet. Minus 58, oops, I gotta actually times those two numbers. This times 58.5 is, and by the way, in these thermal energy transfers, you are going to get really big numbers, but you will see that it all works out. Minus 1059.9. Okay, so that is, now I've dealt with the parentheses accurately. Let me go ahead and do it on this side. It's going to be 418 T final minus, so this times that, and then this times that. 418 times 24.8, and it will be a minus because a minus times a plus is a minus. 10366.4. Okay. Alrighty. So far so good. Now the only thing I need to deal with is this sign. All I'm going to do is get rid of it by multiplying negative times this, which becomes negative 18.119 T final. And a negative times a negative is a positive, plus 1059.9. And now everything is essentially simplified enough so I can continue here. All right, now to solve for T final, which is my only variable, and by the way, that is the answer to my question, I need them to be on the same side. I think it is much easier for me, rather than trying to put them on the left and get a negative number, it makes much more sense to put them on the right and get a positive number. So I'm going to add 18.119 T final to both sides. You're just combining like terms is what they call it in algebra. 18.119 T final. That is 418 plus 18.119 is 436.119 T final. Okay, so that's that term. And now the other term you're going to have to put on the other side. So the constant, the one without the variable, is the has to go on the other side. So since it's a negative here, I'm going to add the same number, so it cancels, to both sides. What I'm just doing here is just classic algebra. So it's just combining like terms so you can isolate a variable. So 10,366.4 plus 1059.9. And I have gotten, so far, 11,426.3. And I know it seems like I'm really far away from getting an answer, but I'm quite close. These big numbers tend to scare people, but it's almost a sign that you're doing it right. It should be big numbers. T final is what I want to solve for. Who's getting in the way? It's this 436. I need to divide both sides by that number. 436.119. Divide by that by both sides. Running out of room here, 436.119. And that will get me an answer for T final. Let me go ahead and put the answer up at the top of the board. T final equals 11,426.3 divided by 436.119. And T final equals 26.26. And remember the unit was degrees C, which it should be. I mean, that was what our temperature units were in. When I gave the question, I believe most of my things were in 3 sig figs. So let's just go with 26.3 degrees C. And that works. Now, there is always a way to test if you were right. The temperature, the final temperature should be somewhere between what the water was and what the silver was. because the silver got a little colder, the water got a little hotter. Don't expect it to be right in the middle. Because water has such a high specific heat capacity, it's going to be able to take in a lot of heat without jumping its temperature up too high. But let's make sure. Yes, the silver was 58.5, the water was 24.8, and as long as it's somewhere in the middle, you're likely correct, especially the way that these answers go. If you're in a reasonable range, chances are you got it right, so that would be a good thing. That's how you do a thermal energy transfer. So for practice, just to make sure that you have this down pat, I could recommend, I'm not sure if I assigned these problems on the homework, but if you were to do another practice problem, you could try practice problem number 66 or 67. I actually think 65, this is almost a reworking of 65, so don't do that one. Do 66 or 67, and you can have some practice. All right, good luck with all of that. I'll see you later. Bye-bye.